Welcome to the series of functions and relations. In this series, we will work on basic concepts and many different types of functions and relations, as well as their transformations through worked examples. In this first session, we will introduce the mathematical language, notation, and functionality concepts. We will also introduce the concept of sets along with their domain and range. In addition, we will illustrate and apply the functionality concepts in worked examples. Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything. Welcome to the series of functions and relations, and this is the first session of this topic. Through this topic, we try to achieve the following tasks: to understand the concept of relations and functions, to learn how to find the implied domain and range of a given function, to understand and work with piecewise-defined function as well as odd and even functions, to find the inverse of a one-to-one function, to understand the definition of a composite function, to understand and describe function transformation and how to use matrices to present it, to apply the knowledge of functions and relations to solve problems. Before showing you worked examples, we here briefly discuss about the domain and range of a function. By definition, the set of all first coordinates of the ordered pair is called domain. In another word, it is the set of possible values the function variable may take. Accordingly, the set of all the second coordinates of the ordered pairs is called range. Actually, a function is a set of ordered pairs in which every x value is paired to a unique y value. Now let's look at the first worked example, which asks us to find the domain of three different functions. The first one is a function of x minus 3 over the sum of x and 2 plus 1 over square root of 1 minus x. According to the rule of this function, it is valid if the denominator of the first term is not equal to 0 and 1 minus x in the square root in the denominator of the second term must be greater than 0. Therefore, we have two simultaneous inequalities established, and the domain of the function is obtained by solving the simultaneous inequalities, which is less than 1 but not equal to negative 2. As for the second function, the rule is square root of logarithm base 0.5 of x minus 1 over x plus 5. Obviously, the outcome of the logarithmic function must be greater than or equal to 0, since it is inside a square root. To make the logarithm base 0.5 of x minus 1 over x plus 5 greater than 0, the logarithmic argument must be between 0 and 1. Hence, we have two simultaneous inequalities established, and by solving them, the domain of x is greater than 1 is obtained. As for the last function, the rule is 1 over square root of logarithm base 0.5 of 2 minus x. Since the logarithm is inside the square root at the denominator, logarithm of 2 minus x to the base 0.5 must be greater than 0. And since the base of the logarithm is between 0 and 1, the argument of 2 minus x must be also between 0 and 1. Hence, we solve the inequality and obtain the domain of the function, which is between 1 and 2, not including the endpoints. Example 2 shows a number of paired equations. The questions are whether the paired equations are the same. Generally speaking, to determine whether if they are the same function, we need to compare the function rule before and after being simplified, as well as their domain and range. For the first question, fx equals x while gx equals square root x squared. It looks like simplifying gx, the square root and the square index can be cancelled. It becomes gx equals x, which is the same as fx. However, when we take a close look at their domain, we find the domain of fx is the entire real number, while the domain of gx is greater than or equal to 0, because the variable x is inside the square root, which must be greater than or equal to 0. Therefore, fx is not equivalent to gx. As for question 2, fx equals modulus x while gx equals the cubic root of x cubed. Now, if we look at their range, it is not difficult to find that the range of fx is greater than or equal to 0, while the range of gx is the entire real number. Therefore, in question 2, fx is not equivalent to gx. For question 3, fx equals x multiplies its modulus, while gx is presented in a piecewise function form. Gx equals x squared when x is greater than 0, and gx equals negative x squared when x is less than 0. After careful inspection, we find that fx is almost the same as gx, except at one point of x equals 0. Obviously, both domain and range of fx are real number, while both domain and range of gx do not cover the point 0, 0. So fx is not equivalent to gx. Here we continue to work on example 2. The pair in question 4 shows that fx equals the quotient of x squared minus 1 and x minus 1, while gx equals x minus 1 under the condition that x is not equal to 1. According to the expression of fx, it can be simplified to x plus 1, and its domain is real number r except the point of x equals 1. Therefore, fx is equivalent to gx. Same rule, same domain and range. In question 5, though gx can be simplified as square root of x minus 1, however, its domain required that x is greater than 1. As for fx, according to its expression, its domain, x is greater than or equal to 1. The difference is that the point of x equals 1 is not included in the domain of gx, while it is included in the domain of fx. So, the pair of equations in question 5 is not equivalent. As for question 6, the easy mistake is to simplify gx to x minus 1. However, the correct approach is that gx should be simplified to modulus x minus 1. Since the rule of both functions are different, so we conclude that fx is not equivalent to gx. There are two logarithmic functions in question 7, in which fx equals 4 logarithm of x to the base e, while gx equals 2 logarithm of x squared to the base e. Though simplified rule of gx may be written as 4 logarithm of x to the base e, its domain is all the real number except the point of x equals 0. However, the domain of fx is greater than 0. Therefore, this pair of functions is not equivalent. As for question 8, gx can be transformed to fx as it can be seen. Hence, we find that the rule, domain, and range of this pair of functions are exactly the same. Therefore, fx is equivalent to gx. In question 9, both fxy and gxy have different rules. Therefore, they have different domains. For gxy, the domain must satisfy the condition of x greater than or equal to -1, and y is greater than or equal to 1. However, the domain of fxy is beyond the domain of gx. It only requires the product of x plus 1 and y minus 1 is greater than or equal to 0. Hence, we may conclude that fxy is not equivalent to gxy. Example 3 is to find the expression of function fx, given that 2fx plus f of 1 over x equals 3x. According to the given criterion, we substitute x by its reciprocal and vice versa. In this way, we have another equation which is 2f of 1 over x plus fx equals 3 over x. Based on the two simultaneous equations, we can take proper steps to eliminate the function of f of 1 over x and find the expression of fx, which is 2x squared minus 1 over x. Example 4 is to find the expression of a linear function fx, given that 3f of x plus 1 minus 2f of x minus 1 equals 2x plus 17. Since fx is a linear function, we may assume fx equals mx plus c. Then our task is to find the values of m and c. The next step is to substitute x by x plus 1 and x minus 1 respectively, and then rewrite the given equation where both m and c are parameters. After being simplified, the expression of mx plus 5m plus c is equivalent to 2x plus 17. Hence, we have two simultaneous equations of m equals 2 and 5m plus c equals 17 established. Therefore, we find m equals 2 while c equals 7. So fx equals 2x plus 7. Example 5 asks us to find the expression of fx, given that f of x plus 1 over x equals x squared plus 1 over x squared. After careful observation, we assume y equals x plus 1 over x. Then we square on both sides of the equation, which comes as the equation of x squared plus 1 over x squared plus 2 equals y squared. Hence, fy equals y squared minus 2, which is equivalent to fx equals x squared minus 2. Example 6 is a similar question of example 5. It asks us to find the expression of fx given the criterion that the f of x plus 1 over x equals x cubed plus 1 over x cubed, as we did in example 5 by assuming y equals x plus 1 over x, and then we cube on both sides of the equation, and it becomes y cubed equals x cubed plus 1 over x cubed plus 3 times x plus 1 over x, all in parentheses. After simplifying the equation, we have fy equals y cubed minus 3y, which is equivalent to fx equals x cubed minus 3x. Example 7 is a logarithmic function, and it asks us to find the expression of fx given that f of 2 over x plus 1 is equal to common logarithm of x. Here we introduce another variable y and assume it equals 2 over x plus 1. Hence, x equals 2 over the result of y minus 1. Now, fy equals common logarithm of 2 over the result of y minus 1, which is equivalent to fx equals common logarithm of 2 over the result of x minus 1, where x is greater than 1. Example 8 presents a function of logarithm base a of a minus a to the x, or in parentheses. The first question is to find the domain and range of the function fx, and the second question is to find its inverse as well as its domain and range. As we know, if the base of a logarithmic function is between 0 and 1, the function is a strictly decreasing function. When the base is greater than 1, then the function is a strictly increasing function. Therefore, both the domain and range of fx here are dependent on the base a. As for question 1, we can see if a is between 0 and 1, both the domain and range are greater than 1. However, if a is greater than 1, both the domain and range of the function fx are less than 1. As for question 2, in order to find its inverse, we exchange the position of x and y. So the new equation becomes x equals logarithm of a minus a to the y to the base a. So we find the rule of its inverse is exactly the same as its original function. Therefore, when a is between 0 and 1, both the domain and range are greater than 1. When a is greater than 1, both the domain and range are less than 1. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.